Let's start today's lecture. This will be on quantum electrodynamics today. Just to recap ourselves, in uh, in the previous lecture, I ended up with writing what I called as the quantum electrodynamics Lagrangian. So let's look into the greater detail, how what each term means, okay, and uh, how does this Lagrangian actually imply that there is a um, electrodynamics picture in what we have been doing actually. Okay, so let's start. So this is actually part one of the quantum electrodynamics. We'll start doing more of this thing in the next 2-3 lectures. So uh, so uh, one second, I'm just not getting something correct. Okay, so what we started off in the previous lecture is a U1 local gauge theory. Uh, 1 second, sorry, what's happening? I pressed something else. Oh god, just give me a second. Okay, so what we started off with is a given local gauge theory, uh, a U1 local gauge theory. So what is a U1? Just it's a unitary group of 1 by 1 dimension. Group of 1 by 1 dimensions, and we'll see higher dimensions in the coming lectures. So 1 by 1, it's just a unitary dimension, so it's essentially a complex number of phase, essentially complex number of unit length. So this U matrix is given just by e power I theta, but then you can put you have to make it local, so I put space, okay, x, so it's a function of space. So at every, so this theta can vary with the space-time point, but even if it varies, what I'm demanding is that it should be the theory should be invariant, the Lagrangian should be invariant, and q corresponds to the charge of the particle actually. So the u1 under the u1 of the u1 charge of the particle, it could be, as we'll see in this particular case, it corresponds to the electromagnetic charge, but it could be any other charge also, but typically let's consider it as the electromagnetic charge. So we were considering scalar field theory, so let's continue with scalar field theory. So L phi, which is a function of del mu phi. Now this L is converted because we want to demand that it should be invariant under U. This just becomes a function of phi and del mu phi. So wherever there is a derivative term, I replace it with capital del, the covariant derivative, and it turns out that the Lagrangian is invariant. And then you also need to add an additional term. So the point we have here is so the Lagrangian of scalar QED, I write it as a QED, is equal to del mu phi star del mu phi minus m square phi star phi minus 1 by 4 f mu nu f mu nu. Okay, so this is the Lagrangian we wrote down last essentially. So now what is the current here in this case? Now we know independently the current. There are a couple of things. Now Noether's theorem is actually valid also for local gauge theories, but the derivation of the current is slightly complicated actually. Okay, so Noether's theorem is also valid for local gauge theories, but not in the present form. Say for example, but not in the, there is something called the theorem 2 of Noether's theorem. Okay, but not really in the present form, but the derivation is complicated. The derivation is complicated. We don't need it actually. Complicated. On the other hand, what we can do, we can start with this and let's look at. So, okay, let's look at how the current is. Okay, because we need to know what is the current which is being conserved, right? Because we know what the current is, but the derivation is. So we just say that okay, I don't use the Noether's theorem, but I'll try to see what is the current for the free case. For the free case, we know that the current is J mu is equal to phi star del mu phi minus phi del mu phi star. In this case, that there are no, meaning it's not locally gauge invariant. So, but in the case of, when I say free, I mean to say global case. In the local case too, this current has the same form. Actually, you can just derive it from the equations of motion. Phi star del mu phi del mu phi star but there is a slight correction here. Okay, so what happens is this J mu, this current now acts as some sort of a source. Okay, so the equation of continuity is not exactly the same form actually as the earlier case. So this equation, okay, so this current acts as a source for the generation of the photon field. Acts as a source for the mu. That means, so if you derive the equations of motion with the full couplings, for the full thing, meaning for this Lagrangian SQED, what you will find, okay, just to revise, okay, I'll just say, okay, revise. So what we have, without any sources, we have the M wave equation is given by box A mu is equal to 0. But the equation which comes out here, because if we start with this particular setup, so there is a mu sitting here also. So for example, there is an mu sitting here also. So what happens is this equation becomes box A mu is equal to J mu, where J mu is equal to this coupling, this current, the current of the matter fields, essentially. Current of the matter fields. Box essentially is del me. Okay, just to revise ourselves, box is del me. Okay. Okay, so this current is still conserved, of course. Current is conserved, but this current is the source of the electromagnetic waves. Okay, so the interactions, the photon field automatically appears by demanding that the symmetric transformation U1 is valid at all space-time points. So this current now is a space-time dependent quantity. So J mu is equal to, say, phi star del mu. Okay, phi minus phi del mu phi star. Now this current would also get modified in the presence of say for example this current. Okay, this is like I wrote the current as though that it is independent of. Now for under gauge invariance, this current is modified because local gauge invariance modifies this current. Okay, this is not really no longer valid under local gauge invariance because of this thing. For global, this current is valid, but local gauge invariance is no longer valid. Now this will become valid because we are demanding at every space-time point this current should be valid, because of the derivative terms is not valid at every space-time point. But now that we are demanding that it should be valid at every space-time point, how does it get validated? Because then it creates a source. It acts like a source for the current density, essentially for the photon field, for the electromagnetic field, essentially. Okay, by acting like a current for the electromagnetic field, by a source current for the electromagnetic field, this just becomes this acts like a what do you call as so this gauge invariance is sort of conserved. So what does gauge invariance mean in terms of conserved quantities or gauge invariance? And this is compensated by the mu field, which also transforms accordingly. Good. So okay, just to go back. So this is compensated by this the transform. So this current, so the current acts like a source. So at every space-time point. Now, what does this local gauge invariance mean? So the local gauge invariance means local gauge invariance means local electric charge conservation. So the correct statement is essentially that the local gauge invariance is essentially is electric charge and current conservation. So at every space-time point, you are demanding that electric charge and current is conserved essentially. At every space-time point, we are demanding electric charge and current conservation. So this is not true in the global case, but now that we are demanding at every space-time point, this current automatically conserves it by introducing a photon field actually. So this is the entire point, that the current automatically this is only be possible if you don't want global interactions. If you want really local interactions, it means that this is only be possible if you have what do you call as local meaning by introducing a local gauge invariance essentially. Yeah. By introducing a photon field actually. So this we have seen now explicitly. Okay, now let's look at so more detail. What is the structure of this particular case, the Lagrangian? So I am repeating the same thing in several different ways so that we understand what we are talking about. Okay, so L SQD is equal to del mu phi star del mu phi minus n square phi star phi minus 1 by 4 f mu nu f mu nu. Okay, now let's do some sort of a understanding what's happening. So phi, let's just say, represents a particle of charge q. So then phi transforms phi prime is equal to e power I theta of x q of phi, and phi star is an antiparticle of phi. So that means phi star prime is equal to e power minus I theta of x q. So phi star has a charge minus q. Charge of phi is equal to q. Charge of phi star is equal to minus q. So, and capital del mu is nothing but del mu plus IE. Now I'll come to what is this IE in a second actually. IE Q A mu. Okay, so let's expand SQD. L sqd is equal to del mu plus IEQ a mu star del mu plus IEQ a mu, okay, minus m square phi star phi minus 1 by 4 f mu nu f mu nu. Now let's me next just neglect the other two terms. Okay, oh, so there is a phi missing here, phi. Okay, so let's consider the first term. So let's consider the first term, which I'll call it as L kinetic of SQD. Okay, so this term, we know that it is gauge invariant because that's how we constructed the entire thing. Okay, has how many terms does it have? So the first term would be, if I expand this, del mu phi star del mu phi. Okay, there's something surprising in it. It's exactly like, okay, the kinetic term of the scalar field. So the next term would be plus IEQ a mu phi star del mu phi. Okay, then another term would be okay, the other term would be del mu phi star, okay, times IE a mu phi, and the last term would be E square Q square a mu, okay. IEQ del mu phi star a mu phi minus E square Q square a mu phi star phi. Okay, and this is just the kinetic part. So this part is just exactly, now if I add these two parts, these exactly like the Klein-Gordon equation, and this part is the pure electromagnetic equation, okay, for the photon fields. So what is this remaining part? The remaining part, what is this remaining part? So this is the remaining part, which is interesting actually for us. So the remaining part comes out automatically. So you have two distinct fields, okay. So there are these a mu fields which came automatically, okay, and then there are this, so independently you can write for electromagnetic theory, you can write an Lagrangian, but this Lagrangian came automatically to us because we didn't start with electromagnetic theory, we started with the U1 theory. But it turns out that this U1 theory, if I make it locally gauge invariant, it is automatically a theory of electromagnetism, okay, just by demanding that it should be local, okay, this gauge invariance should be local, it is automatically a theory of electromagnetism. Then you consider the scalar field theory, then the scalar field theory, make it get local, automatically gives you electromagnetic theory, and then it also gives you the interactions between electromagnetic theory or the particle and also the particle and the photon field. So let me write it this parts in terms of, so L sqd now can be written as L sqd is equal to del mu phi star del mu phi minus m square phi star phi. This is the first part. The second part is minus m f mu nu. This is the second part, And the third part I call it as L interaction, and L interaction is, so IEQ phi star del mu phi minus phi del mu phi star minus E square Q square A mu phi star phi. One of them should be a minus sign because there is a star actually. Okay, now what is this? Okay, there is an mu here somewhere. IE IEQ mu. Now this is nothing but your J mu. So this is nothing but IEQ A mu J mu minus E square Q square A mu phi star phi. Okay, so for the first time what we have seen is the interactions between particles. So what we got, not only a free theory of theory of electromagnetism, but we also got how these particles, say for example, this is spinless electrodynamics, say for example. So this also can be called as scalar electrodynamics, spinless electrodynamics. It has several, you can call it in a number of names. Okay, so we also got how the interactions happen between particles, between different kinds of particles essentially. So here electromagnetic interactions happen between the phi fields. For the scalar fields, how does it experience electromagnetic interaction? It experiences electromagnetic interactions through A mu. Okay, so it experiences electromagnetic interactions through okay, through the photon field. Now let's look at a couple of points again here. All the interactions which we know in nature appear as current and current interactions. You see this A mu is, which is like a 4 vector, is also exactly transforms like a current. Okay, exactly transforms like a current. Okay, let's look at L interaction again in more detail. Is equal to, so this is IEQ, okay, A mu J mu. So this is minus E square Q square A mu phi star phi. Now this is a current interaction. All the interaction in nature appear as current interactions. So the current here is made up of scalar field current, and this is a vectorial current, vector field, but this you can think in terms of, if you call it as a current, so this is essentially a vector field essentially. So it's like a vector field current actually, the field of a vector field, the current of a vector field. But okay, let's say, so all the currents, as we know from Lorentz, meaning when we did the scalar field theory and also from the Dirac equation, all the currents transform as 4 vectors, no, essentially A mu's. Okay, so this is a current interaction with A mu. So this is your Lagrangian interaction. Now how does it interact? This is the how this is this term which I said I'll be looking into saying it a number of times. This term is the strength of the interaction. Okay, this is the strength of the interaction. This is called the coupling constant. So the strength of the interaction is determined by two things. One is the charge of the particle as well as the strength of the interaction, which in the case of electromagnetic theory is just E. Okay, normalized in terms of units of electric charge. Okay, okay, so this is the interaction part of the Lagrangian. So this interaction is always given in terms of current interaction. Now this coupling constant should be equivalent to the coupling constant which we know, actually, which should be equivalent to the coupling constant of the electromagnetic theory, which we know, we say it's alpha from atomic theory. This is equal to E square by 4 pi, and that is equal to 1 by 137 at atomic scales. So Q okay, I'll come to that in a second. Okay. So the coupling constant is determined in terms of this. So E is nothing but square root of 4 pi is equal to square root of 4 pi alpha, that is equal to alpha is equal to, where alpha is equal to 1 by 137, which is a small quantity. This is a very small quantity. 1 by 137 is actually reasonably small quantity. So this coupling constant is reasonably small, so you can start dealing things in perturbation manner. Can start computing things, cross sections, amplitudes. What I mean to say is computing amplitudes in a perturbative fashion. Okay, so you can actually compute it using perturbative theory. Now you see a very interesting thing. The first term is order 1. It's the first order. It's a leading order in perturbation theory, whereas the second term has E square. Okay, has E square. So this is second order in perturbation theory. The E square term, this E square term is second order in perturbation theory. Okay, so at the leading order you can neglect any interactions coming from E square, because we only are worried about the leading order if you want to deal it with perturbation theory. So you can neglect the second term and you can only work with the first term and see how the various cross sections will appear, meaning how you can estimate how various cross sections appear. Okay. 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 So now let's, before going to the cross sections, let's try to understand what is this field A. Okay. Before further proceeding, computation across sections. Let's understand what's a mu. See, I said in the classification of particles when I did it, so I said that a mu is a spin 1 particle. Okay, I said that a mu is a spin 1 particle, and when I did that, that was some time ago, actually, in one of these lectures, when I did that all the particles come out as some representations of some Lorentz group, this thing. I mentioned that that a mu is nothing but it's a spin one. It represents a spin. It's a okay. Now the question is, what are its wave functions? So what are its solutions? Okay, what is it? So far we have not seen any spin one particle in the later on when we did the equations of motion. For all the particles, we started that all matter particles are spin half, or if you neglect the spin, it is spin 0. So that is what we are trying to do actually. So we claim that now by imposing the condition that all the matter particles all the matter particles have electromagnetic charge conservation at every space-time point, which is equivalent to saying that the UN charge is conserved at every space-time point. I am already introducing the first spin 1 particle which we have seen so far. We haven't seen any spin 1 particle. Okay, we haven't seen any spin 1 particle so far. So a mu is the first spin 1 particle. In nature, actually, only if you neglect the spins of the particle, you have spin 0. So most of the things which we know are essentially fermions. All the matter particles are essentially fermions. So, but now you have a spin 1 particle for a mu. Okay, a mu is the first spin 1 particle which we are seeing, and this comes as a consequence, appears as a consequence of local gauge invariance. Because I am insisting local gauge invariance, it appears, and that's the reason why these a mu's are also called gauge bosons. It's a boson because it's spin it's an integer spin. Okay, it's not spin half, meaning it's not a fermion, so it's not half integer spin, and that's the reason why we call it as a gauge boson, because it comes, this boson or a mu appears purely to satisfy the local gauge invariance, at least the way we want to see it in this particular domain. So that's the reason why these are called gauge bosons. Okay, so these are called gauge bosons, and the first example which we are seeing is essentially of this particular field, which is a mu field. So what is this a mu, which we'll identify with photon actually? So a mu, what are its equations of motion? Okay, and what are its what are its equations of motion, and what is its what do you call what are its wave functions? Okay, the solutions of these equations of motion. That's what we'll look into it actually. Okay, so let's just look at the equations of motion. The equations of motion can be derived from the Lagrangian, which I have already identified it to you. Okay, so okay, so uh, the Lagrangian of electromagnetic theory is the same as the Lagrangian of the photons. So this is Em is minus 1 by 4 f mu nu, where f mu nu, I'll write it down for you again, a nu minus del nu a mu. Now this is essentially gives you the equations of motion as this gives you the Euler-Lagrange equations of motion as box a mu is equal to 0 for the free case, essentially for the free case. So the free case, this has solutions, box is equal to nothing but del square. So this has solutions, a mu is equal to which is a solution of polarization and momentum. Say for example, is equal to epsilon mu, okay, e power I k px, some plane wave part, and epsilon mu. This epsilon mu is called the polarization vector. So just like the spinors, the polarization vector also has 4 degrees of freedom. Okay, epsilon mu is equal to epsilon 0, epsilon 1, epsilon 2, epsilon 3. Okay, now there are some conditions on this epsilon mu. Okay, so first of all, photon is massless. So if you have any momentum, essentially the momentum of the photon p square, the 4 momentum of the photon is always equal to 0. Is always equal to 0. Why? Because it's massless. Okay, so you have, if you take any photon and take the 4 momentum of it, so a mu, which is a function of epsilon and p, always p square is equal to 0, where p is the mass of the p square is the 4 momentum of the photon. P square is equal to p mu. Okay, always. Okay, then there is the second condition on the photon, that it turns out that it is always transferred to the direction of momentum. So for example, the polarization vector should be always be transverse. This comes out in from the gauge conditions. Essentially can show that so using the gauge conditions, okay, you have an equation like del mu a mu is equal to 0. This comes from because you can choose a gauge transformation, okay, in such a way that you can have okay, there is some equation of this particular, so the momentum of the photon so essentially if you write the momentum, if you take the momentum and the photon, their inner product should always go to 0. And if you write it in terms of this solutions, say for example if you write it in terms of momentum space, so this just becomes k mu epsilon mu is equal to 0. So this essentially tells you that epsilon mu is always, okay, I used p mu, right, for the momentum. So let me say if p mu is the direction of the momentum of the photon, so epsilon mu p mu is always perpendicular to the direction of p mu. So this gives you one condition. Then there is the p square is equal to 0. This also gives you second condition for the massless particles. And so this okay, the p square is equal to 0 is also related to something, some gauge condition also. But anyway, there is also another gauge condition. If I replace a mu, this is the classical condition which you know, that if you write a mu and a mu plus some del mu some zeta, say for example, where del square zeta is equal to 0, okay, as long as this is true, the Lagrangian is invariant. So a mu is not unique solution. So the a mu is not an unique field actually, because it's a gauge field. A mu can always be, you can always add another derivative of some scalar field, okay, of some scalar field. So this is called the gauge condition. You can always add this, and the entire theory is completely invariant. So if you replace a mu with a mu plus del mu of phi, such that xi and del square is equal to 0, okay, and what happens is you get this, the entire theory is invariant. This condition is called the gauge condition. This is very similar to what you have also in classical electrodynamics, right? In classical electrodynamics, you have the condition that if you replace A going to A plus del psi or del phi or something, okay, whatever, some potential, and phi with phi minus some the time derivative essentially, so grad phi. So very similar to that essentially. So this is the Lagrangian is invariant, and so all the consequences of the Lagrangian. So for example, the equations of motion and solutions. Well, let me not say this not there. Okay, so the equations of motion. So this is reminiscent. This is exactly like in classical electrodynamics. You have the condition that you can have always that A. This is also called the gauge condition plus del phi, and then accordingly. Now I need to introduce some other term. So del some scalar field phi xi eta, let me call it as eta, okay, and then phi goes to some phi. This should be a derivative with the time. So phi del eta by t, okay, something like this. So if you do these transformations, classical electrodynamics is invariant, okay. So the same thing what we are trying to do is exactly in the same manner. So but this appears as something called the gauge condition. So there is a lot of freedom in choosing what is a mu is, okay. So this freedom is called the gauge freedom. So you have some freedom up to a scalar field, derivative of a scalar field, okay, for this a mu, okay, just like, okay. So the a mu itself has a freedom as long as you have del square xi is equal to 0. A mu has some freedom, and this is called the gauge condition. So you can use these two conditions, like for example that p mu epsilon mu is equal to 0, And the gauge condition, actually this is also related to p square is equal to 0. If you, for massless particles, it is always true actually. Okay, one cannot just say that this is true. So using the conditions 1 and 2, so you can get rid of the four conditions. Say for example, of the four degrees of freedom in a mu, of the four possible degrees of freedom in a mu, we can get, or epsilon mu actually, get rid of two of them. So essentially, so though we started with 4 degrees of freedom, because a mu is massless, because for massless particles, and also for the condition that there are always transfers, it turns out actually that all the massless gauge bosons have only 2 degrees of freedom actually. So there are only 2 degrees of freedom. All massless gauge bosons have only 2 degrees of freedom. Okay, all massless gauge bosons have only 2 degrees of freedom. This is a very important result. So these are essentially all spin 1. So gauge bosons are typically spin 1 particles like you've seen, and because the photon is massless and it has these conditions of the gauge degrees of freedom, and also that it transfers into the direction of the polarization vector. So and it's massless, all these things put together, you can actually, so the massless condition is very important actually, and so is the gauge degree, the transverse direction. So these two will put to the condition that there are only 2 degrees of freedom. That means epsilon mu has only 2 polarizations, which are both transverse to the direction of this thing. Say for example, if p mu is equal to pz by c, say c, we can set it to 1. Okay, pz by c, so pz, say for example mod pz 0 0, and say so moving in the z direction, say for example, okay, pz. Okay, so p mu is pz. So what will happen to the two polarizations? The two polarizations epsilon mu, which will be are 1 0 1 0, and then other one would be 1 1 0 0. So there won't be anything in the x direction, in the z direction. So the photon would be moving in the z direction. Say for example pz, this is z direction. The other two polarizations would be in x and y direction. So which will be just transfers to the degree of direction of the propagation of the photon actually. Then similar to this, you also have the completeness degrees of freedom. The epsilon mu has also completeness relations, which you have to have. So it's similar to what we had essentially. So they form, they are normalizable. Okay. okay, they are normalizable. So the polarization wave functions are the polarization wave functions are normalizable. So you can make a complete orthonormal basis set, okay, of these wave functions, okay. So these are important points actually, that mm, okay. So what we, just to summarize, that we had two conditions. It has only, in principle, it has four uh, ca- four degrees of freedom, the photon field. The Lorentz gauge essentially, one of the degrees of freedom is goes away because q square is equal to 0, because or p square is equal to 0. But it has 4 degrees of freedom, but the 4 degrees of freedom being that you can always choose that the 2 degrees of freedom are meaning you can always, because this massless field, you can always choose some sort of a gauge in which uh, uh, the condition that one of the degree of freedom can be completely rotated away, or this is also possible only for massless degrees of freedom, okay. Okay, and so you can, in principle, you can choose something called uh, what do you call, uh, what do you call actually is that there are circular polarizations possible if you have something called non-covariant gauges, okay. I didn't go into that, but anyway, so just to say that we have uh, this particular meaning, just to say that using the conditions that um, um, using the conditions of the masslessness and the gauge properties of the photon field, you can show that it has only 2 degrees of freedom, and that's because it's only traveling always its polarization vectors are always parallel to the direction of the propagation, always perpendicular to the direction of propagation. So these four vectors, epsilon mu nu, also form, like I said, um, this what you call as complete set, so orthonormal set. So this means that if you call if one of them essentially is as R and S, say for example 1 and 2, so we have epsilon 1 of P dot epsilon 2 of P, okay, or epsilon is equal to 0, okay, and epsilon 1 dot epsilon 2 is nothing but what do you call, okay, you can say epsilon 1 dot 1 is equal to 1 and epsilon 2 dot 2 is equal to 1, so you can re-express it in terms of epsilon R dot P dot epsilon S dot P is equal to delta RS, say some up to certain constant essentially. And then you also have these are orthonormal relations. Then you have the other condition that sum or all epsilon mu of p times r, okay, and then epsilon nu r sum or all r is equal to eta mu. Okay, so this is these are just this I gave you for completeness relations, that these are a complete set of complete set of wave functions which are orthonormal, which are complete set of orthonormal wave functions. This minus sign depends upon the convention. Let me just write it as epsilon mu. Okay, so this photon field is really so the properties of the photon field are sort of fixed by its gauge degrees of freedom and also by its massless nature. Okay, so this part one has to understand. So for every massless gauge boson, this is always true, that it is always given in terms of this 2 degrees of freedom. So finally, let me just write down what happens with fermions and electromagnetic theory. So again, I'll define. Now I know that how do I write an electromagnetic theory? If I just write an UN invariant theory, it gives me the electromagnetic theory. So let's write down the Lagrangian for actual QED. Okay? Actual QED means electrons. A theory, QED is a theory of electrons and photons. So let's write down this theory for the theory of electrons and photons. So how do you write it down? I write it down by just imposing the human interactions. So I have psi is a Dirac fermion. That's it, and I'm just going to impose the human local gauge invariance for this Dirac fermion. So psi prime, psi will be replaced by psi prime, which is equal to e power I theta of x q psi of x. Okay, psi of x. Okay. Now whenever now I know the prescription, but that whenever there is a derivative, I just reimpose by del mu. This del mu plus I e q a mu. So that the Lagrangian would be invariant. So the free Lagrangian, so L Dirac or curly L Dirac is I psi bar del mu gamma mu. So I wrote it as del slash minus m psi. That's it. Okay. Now, so it's such a nice theory that now I have LQD is equal to I psi bar del slash minus m psi minus 1 by 4 f mu. Okay, isn't it wonderful that I wrote this in one single step? Okay, I didn't have to do anything, because all of the things which we know the technique, we know the Lagrangian, and we know how to get it done. So at one shot, without actually showing what's happening, meaning I showed that this is your QED Lagrangian. Okay, so good. So we'll stop here, and then we will see. I'll maybe um, how do you show the gauge invariance of this particular case? So I want you guys ask you essentially explicitly try it out, see how you show the gauge invariance in this case for the fermions. Try it out explicitly how psi transforms, how psi bar transforms, and how a mu transforms, and don't show explicitly that this QED Lagrangian is gauge invariant. Okay, we know all the techniques. I'll try to do it also in the next lecture essentially, but this is your QED Lagrangian, and we'll start doing the QED part uh, in greater detail in the next lecture actually.